Let me ask you just on this tension. We've been dancing between physics and mathematics. What to you is an interesting line you can draw between the two? You have done some very complicated mathematics in your life to explore the laws of nature. What's the difference between physics and mathematics to you?
Well, I love math. I think my first love is physics, and the math that I've done to because it was needed
Mm. In service of physics.
in service of physics. But then, of course, in the heat of it, it has its own appeal, and
In the heat of it, I like it. Sure.
it has its own appeal, and I certainly enjoyed it. And ultimately, I would like to think, I wouldn't say I believe, but I would like to think that there's no difference between physics and mathematics, that all mathematics is realized in the physical world, and all physics has a firm mathematical basis, that they're really the same thing. I mean, why would there be math that had no physical manifestation? It seems a little odd, right? You have two kinds of math, some that are relevant to the real world.
Well, they don't have to be contradictory, but you can have can't you not have mathematical objects that are not at all connected to the physical world? So, I mean, this is to the question of, is math discovered or invented? So to you, math is discovered,
Yeah.
and there's a deep linkage between the two.
Yeah.
Do you find it at all compelling, these ideas, like something like Max Tegmark, where our universe is actually fundamentally a mathematical object? That our universe is mathematical, fundamentally mathematical in nature.
My expertise as a physicist doesn't add anything to that. It's not really, physics is, I was once very interested in philosophy and, physics, I like questions that can be answered, that it's not obvious what the answer is, and that you can find an answer to the question and everybody will agree what the answer is, and that there's an algorithm for getting there. Not that these other questions aren't interesting, and they don't somehow have a way of presenting themselves, but to me, the interesting thing is motion in what we know, is learning more and understanding things that we didn't understand before, things that seemed totally confusing, having them seem obvious. That's wonderful. So I think those questions are there. I mean, I would even go further, the whole multiverse. I don't think there's too much concrete we're ever going to be able to say about it.
This is fascinating because you spend so much time in string theory, which is devoid from a connection to the physical world for a long time. Like not devoid, but it travels in a mathematical world that seems to be beautiful and consistent, and seems to indicate that it could be a good model of the laws of nature. But it's still traveling independently, because it's very difficult to experimentally verify.
Well,
but there's a promise laden in it, in the same way multiverse, or you can have a lot of kind of very far out there questions where your gut and instinct and intuition says that maybe in 50, 100, 200 years, you'll be able to actually have strong experimental validation, right?
I think that with string theory, I don't think it's likely that we could measure it, but we could get lucky. In other words, just to take an example, about 10 or 20 years ago, it was thought that they had seen a string in the sky, and that it was seen by, doubled stars that were gravitationally lensed around the gravitational field produced by some long string. There was a line of double lensed. Now the signal went away, okay? But people were hoping that they'd seen a string, and it could be a fundamental string that had somehow gotten stretched, and that would be some evidence for string theory. There was also bicep 2, which the experiment was wrong, but it could have happened. It could have happened that we got lucky and this experiment was able to make direct measurements. Certainly would have been measurements of quantum gravity, if not string theory. So it's a very logical possibility
Sure.
that we could get experimental evidence from strings. That is a very different thing than saying, do this experiment, here's $1 billion, and after you do it, we'll know whether or not strings are real. But I think it's a crucial difference. It's measurable in principle, and we don't see how to get from here to there. If we see how to get from here to there, in my eyes, it's boring, right? Mm-hmm. So when I was a graduate student, they knew how to measure the Higgs boson. It took 40 years, but they did it. Not to say that stuff is boring. I don't want to say that stuff is boring. Yeah. But when Magellan set out, he didn't know he could get around the world. There was no map. Yeah. You know? So I don't know how we're gonna connect in a concrete way all these ideas of string theory to the real world. And when I started out in graduate school, I said, what is the most interesting problem that there might be, the deepest, most interesting problem that there might be progress on in 60 years? And I think it could be, that, in another 30 years that maybe we'll learn that we have understood how black holes store information. That doesn't seem wild, that we're able to abstract what we learned from string theory and show that it's operative and the Bose-Einstein condensate they did, if you when Bose and Einstein predicted it, when was that? The 30s, maybe early 30s. There were 20 orders of magnitude that were needed in order to measure it. And they did 50 years later. So, and then you couldn't have guessed how that had happened, how they could have gotten that. And it could happen that I don't think we're going to see the heterotic string spectrum at an accelerator, but it could be that things come around and in an interesting way, and somehow it comes together. And the fact that we can't see to the end isn't a reason not to do it. We're just, what did they do when they were trying to find the Pacific, right? They took every route. They just tried everything. And that's what we're doing. And I'm taking the one that my nose tells me is the best, and other people are taking other ones. And that's good, because we need every person taking every route. And, if somebody on another route finds something that looks really promising, I'm going to make a portage over the mountain and get on their stream, So the fact that you don't see the experiment now isn't, to me, a reason to give up on what I view as the most fundamental paradox in 21st century physics.
Absolutely. You can see that it's possible. You just don't know the way. But that's what I mean, why some of the philosophical questions could be formulated in a way that's explorable scientifically. So some of the stuff we've talked about, but, for example, this topic that's become more okay to talk about, which is the topic of consciousness. To me as an artificial intelligence person, that's a very practically interesting topic. But there's also philosophers. Sean Carroll loves to argue against them. But there's some philosophers that are panpsychists.
I'm not against philosophers. It's just not as fun.
It's not as fun. All right. But they start a little flame of a fire going, that some of those flames, I think, eventually become physics. So eventually become something that we can really like. Having them around is really important because you'll discover something by modeling and exploring black holes that's really weird. And having these ideas around, like the ideas of panpsychists that consciousness could be a fundamental force of nature, just even having that crazy idea swimming around in the background could really spark something where that you were missing something completely.
Mm.
And it's just that's where the philosophy done right,
Mhm.
I think, is very useful. That's where even the these thought experiments, which is very fun in the sort of the tech sci-fi world that we live in a simulation, uh, that taking a perspective of the universe as a computer, as a computational system that processes information, which is a pretty intuitive notion, but you can just even reframing it that way for yourself could really open up some different way of thinking.
Could be.
And then you have I don't know if you're familiar with Stephen Wolfram's work of like cellular automata and complexity.
Yeah. I did a podcast with Stephen.
Who's Steven? That's awesome. I mean, to me, forget physics, forget all that. Cellular automata make no sense. They're so beautiful. They're so
They are.
that from
They're
simple
really
rules you
incredible.
can create complexity. I just don't think he wrote a book, A New Kind of Science, um, basically hinting at, which a lot of people have hinted at, is like we don't have a good way to talk about these objects. We can't figure out what is happening here. These
Yeah.
trivial rules can create incredible complexity.
He's totally right about that. Yeah.
And physicists, I guess, don't know what to do with that. Don't know what to do with cellular automata because you can describe the simple rules that govern the system, but
Right.
how complexity can emerge, like incredible complexity.
Yeah. Of course, Wolfram's version of that is that physicists will never be able to describe it.
Right. Yeah, exactly. He tries to prove that it's impossible. What do you make of that? What do you make about the tension of being a physicist and potentially not being able to? It's like Freud or somebody that maybe Sigmund Freud that maybe you'll never be able to actually describe the human psyche. Is that a possibility for you? That you will never be able to get to the core fundamental description of the laws of nature?
Yeah. So I had this conversation with Weinberg.
Yeah. How did it go?
So Weinberg has this book called Dreams of a Final Theory.
Yeah.
And I had this conversation with him. I said, why do you think there's ever going to be a final theory? Why should there ever be a final theory? I mean, what does that mean? Do physics departments shut down? We've solved everything. And, what is it? Doesn't it seem that every time we answer some old questions, we'll just find new ones and that it will just keep going on forever and ever? And he said, well, that's what they used to say about the Nile. They were never going to find the end. Then one day they found it.
Yeah.
So I don't know. String theory doesn't look like a candidate to me for a final theory.
As it stands now. It doesn't get to the bottom of the well, into the sides, into the whole.
Yeah, it seems to me that even if we kind of solved it and we've did experiments, there still would be more questions, like why are there 4 dimensions instead of 6? It doesn't seem to have anything that in it that would explain that. You can always hope, that there's something that we don't know about string theory that will explain it, but it still doesn't look like it's going to answer every question. And why is there 1 time, not 2? Why is there? It doesn't seem like it's. I don't even know what it would mean to answer every question.
Well, to answer every question, obviously. So when you refer to the theory of everything, you'll be able to have if it exists, it would be a theory that allows you to predict precisely the behavior of objects in the universe and their movement, right? What about them? Their movement.
Yeah.
Like precisely, no matter the object.
Right, that's true. So that would be a really interesting state of affairs if we could predict everything but not necessarily understand everything. So, for example, let's just forget about gravity. I mean, we're not too far from that situation. If we forget about gravity, the standard model, in principle, given a big enough computer, predicts almost everything. But if you look at the standard model, it's kind of a laundry list with neutrino masses and all that stuff. There are hundreds of free parameters. Where do they come from? Is there an organizing principle? Is there some further unification?
Sure.
So being able to predict everything is not the only goal that physicists have.
Mm-hmm. So on the way to trying to predict, you're trying to understand. That's actually probably the goal, is to understand.
Yeah. But right, we're more interested in understanding than actually doing the predictions. But the predictions are more focusing on how to make predictions is a good way to improve your understanding because you know you've understood it if you can do the predictions.
Yeah, one of the interesting things that might come to a head with is artificial intelligence. There's an increasing use of AI in physics. We might live in a world where AI would be able to predict perfectly what's happening, and so that will, as physicists, you'll have to come to to the fact that you're actually not that interested in prediction. I mean, it's very useful, but you're interested in really understanding the deep laws of nature versus a perfect predictor.
Yeah.
Like you want to play
but
chess.
Even within AI people are trying to understand what it is that the AI bots have learned in order to produce whatever they produce.
For sure, but you still don't understand deeply, especially because they're getting, especially language models. If you're paying attention, the systems that are able to generate text, they're able to have conversations. ChatGPT is the recent manifestation of that. They just seem to know everything. They're trained on the internet. They seem to be very, very good at something that looks like reasoning. They're able to generate. You can ask them questions. They can answer questions. It just feels like this thing is intelligent, right? And I could just see that being possible with physics. You ask any kind of physical question, and they'll be able to very precise about a particular star system or a particular black hole. It'll say, "Well, these are the numbers." It'll perfectly predict, and then sure you can understand how the neural network is, the architecture is structured. Actually, for most of them now, they're very simple. You can understand what data is trained on, huge amount of data. You're giving it a huge amount of data from a very nice telescope or something. And then, but it seems to predict everything perfectly. How a banana falls when you throw it. Everything is perfectly predicted. You still don't have a deep understanding of what governs the whole thing. And maybe you can ask it a question. It'll be some kind of Hitchhiker's Guide to the Galaxy type answer. It's a funny world we live in. Of course, it's also possible that there's no such deep, simple governing laws of nature behind the whole thing. I mean, there's something in us humans.
It's possible
that wants it there to be.
Yeah,
but doesn't have to be, right?
Right.
I do. Where do you, again? You're betting you already bet the farm. But if you were to have a second farm, do you think there is a theory of everything that we might get at? So simple laws that govern the whole thing.
I don't. Honestly, I don't know, but I'm pretty confident that if there is, we won't get to it in my lifetime. I don't think we're near it.
But doesn't it feel like there is, like the fact that we have the laws we do, they're relatively simple already. That's kind of incredible. It's just there seems to be simple laws that govern things, right?
By a theory of everything, you mean a theory of everything, an algorithm to predict everything.
But a simple algorithm.
A relatively simple algorithm to predict everything. So for me, it would be a sad day if we arrived at that without answering some deeper questions.
Sure, of course. It definitely is. But the question, yes. But one of the questions before we arrive there, we can ask, does such a destination even exist? So, because the asking the question and the possible answers and the process of trying to answer that question is in itself super interesting. Is
Yeah.
that is it even possible to get there where there's an E equals MC squared type of, there's a function. Okay, you can have many parameters, but a finite number parameter function that can predict a lot of things about our universe.
Well, okay, but just to sort of throw one thing in order to answer every question, we would need a theory of the origin of the universe.
Right.
And that is a huge task, right? So, and the fact that the universe seems to have a beginning defies everything we know and love, right? Because we you know, one of the basic principles of physics is determinism, that the past follows from the present follows from the past, the future follows from the present, so on. But if you have the origin of the universe, if you have a big bang, that means before that there was nothing. And you can't have a theory in which something follows from nothing. So somehow,
Sounds like you don't like singularities.
well,
I thought for somebody that works with black holes, you would get used to them by now.
no, I like this because it's so hard to understand.
Yes.
I like it because it's hard to understand, but it's really challenging us.
Yes.
It's not I don't think we're close to solving that problem.
So even
And string theory has basically had nothing. There's been almost nothing interesting said about that in the last many decades.
so string theory hasn't really looked at the Big Bang. It hasn't really tried to get to the origin.
Not successfully. There aren't compelling papers that lots of people have read that people have taken it up and tried to go at it, but there aren't compelling. String theory doesn't seem to have a trick that helps us with that puzzle.
Do you think we'll be able to sneak up to the origin of the universe, like reverse engineer it from experimental, from theoretical perspective? Like, okay, if we can, what would be the trajectory?
You've already gotten yourself in trouble, you see, because you used the word reverse engineer.
Sure.
So if you're going to reverse engineer, that means, you forward engineering means that you take the present and determine the future. Reverse engineering means that you take the present and determine the past.
Yeah.
But
estimate the past. But yes, sure.
But if the past was nothing, how are you ever going to reverse engineer to nothing?
Well,
that's hard to do.
Run up against the nothing, right? Until have mathematical models that break down nicely to where you can actually start to infer things. Do you think?
Let's work on it.
No, but do you think that
it could maybe, but it is. People have tried to do things like that,
yeah,
but
have not succeeded.
It's not something that we're getting A+ in.
Sure. Let's pretend we live in a world where in 100 years we have an answer to that.
Yeah.
What would that answer look like? What department is that from? What fields led us there? What not what fields, what set of ideas in theoretical physics? Is it experimental? Is it theoretical? Like, what can you imagine could have possibly lead us there? Is it through gravitational waves and some kind of observations there? Is it investigation of black holes? Is it simulation of universes? Is it maybe we start creating black holes somehow? I don't know. Maybe some kind of high energy physics type of experiments.
Well, I have some late night ideas about that aren't really ready for prime time.
Okay, sure, but you have some ideas. Okay.
Yeah, but and many people do. It could be that some of the advances in quantum information theory are important in that they kind of go beyond taking quantum systems and just replicating themselves, but combining them with others.